Welcome to the presentation of our CVPR paper, Floxels, Fast Unsupervised Voxel-Based Scene Flow Estimation. In this work, we investigate the problem of scene flow estimation. But before diving into the details, what exactly is scene flow estimation? Scene flow estimation describes the task of estimating the motion of points in between two consecutive point clouds. Scene flow estimation methods can be broadly categorized into two main classes, supervised and unsupervised approaches. In this work, we concentrate on unsupervised scene flow estimation. We introduce a novel unsupervised method called Floxels, short for flow voxels. The most relevant prior work is the unsupervised method fast neural scene flow. Fast neural scene flow takes the point cloud at time t0 as input during inference. More specifically, each point is processed individually and is represented by its x, y, and z coordinates. These coordinates are passed through an MLP, which predicts a flow vector for each point, consisting of velocities in the x, y, and z directions. By applying these flow vectors to the points in the point cloud at time t0, the method generates an estimated point cloud at time t1. To train the MLP, a loss is computed based on the distances between each warped point and its nearest neighbor in the actual point cloud at t1. This method achieved strong performance at the time of its publication and, most importantly, significantly improved the runtime compared to previous unsupervised approaches. Unfortunately, in many cases, the flow estimates produced by fast neural scene flow are far from satisfactory. In our error analysis, we identified several recurring failure modes and limitations of fast neural scene flow. We observe false correspondences. The method often converges to false points. This seems to stem from a strong bias towards the nearest neighboring points, ignoring the fact that nearby points typically move in similar directions. We observe error in occluded regions. For example, here, the highlighted region shows a wall, which is occluded by the tree for one of the 2 point clouds. Fast neural scene flow incorrectly predicts large motion for these points that are visible only in one of the 2 frames. We observe non-local interactions. The method sometimes fails to estimate the flow correctly when 2 objects pass close to each other but move in opposite directions. And we also observe artifacts in empty regions. When visualizing the estimated flow fields from a bird's eye view, we observe significant flow in empty areas of the scene. And finally, the runtime of fast neural scene flow and the current state-of-the-art method Euler flow is often too high for practical deployment in real-world systems. Floxels mitigates these problems. Floxels relies on motion patterns of neighboring points, which prohibit converging to nearest but incorrect points. Floxels is more robust to occlusions and minimizes the non-local interaction problem by restricting influence to small regions. Also, Floxel does not hallucinate motion patterns in empty regions. And finally, Floxels is significantly faster. As we'll see later, Floxel not only outperforms fast neural scene flow on standard benchmarks, but also approaches the performance of Euler flow, the current state of the art, while operating at a fraction of the runtime. So, what makes all of this possible? Instead of using an MLP to learn the flow field and represent space, as done in fast neural scene flow, Floxels employs a voxel grid. This voxel grid spans the entire 3D space of the scene, and each vertex contains 3 learnable parameters corresponding to the flow in the x and y and z directions. To estimate the flow at any given point, we use trilinear interpolation. As a result, only nearby vertices influence the flow prediction for a given point, effectively eliminating non-local interactions. Moreover, using a voxel grid simplifies and speeds up the optimization process. The second major component of Floxels is its multi-frame loss. Instead of computing the loss based solely on 2 consecutive frames, Floxels incorporates m past and m future frames into the training objective. This design has several key advantages, most notably improving flow estimation in occluded regions or areas with missing points. The third and final component is a cluster loss, which encourages spatially close points to move in similar directions. However, clustering distinct objects together can degrade performance. To avoid this, we select parameters that deliberately over-cluster, reducing the risk of combining unrelated objects. This loss component helps to reduce false associations, where points incorrectly converge towards unrelated nearby points, ignoring the motion pattern in their vicinity. By now, we have seen instructive qualitative examples and runtime measurements of Floxels, but how does Floxel compare quantitatively with other approaches? To answer this, we evaluate Floxels on the Argoverse 2 Scene Flow Challenge benchmark. We report mean dynamic normalized endpoint error, the prime metric used in the benchmark. Supervised methods are shown with hatched bars, while unsupervised methods are shown with solid bars. We include 3 results for Floxels using 5, 9, and 13 frames. Among all unsupervised methods, only Euler flow outperforms Floxels. However, as we discussed earlier, Euler flow is 60 to 114 times slower than Floxels. Floxels not only surpasses all unsupervised methods except for Euler flow, but also outperforms several recent supervised approaches. In summary, we propose Floxels, a novel unsupervised flow method that is significantly faster than previous approaches. Voxels addresses many of the key limitations found in earlier unsupervised methods. And most importantly, we demonstrate that Voxel outperforms all prior unsupervised flow techniques, except for Euler flow, which achieves slightly better results but at a much higher computational cost. For more details, please refer to our paper. Thank you for watching. You can find the paper scanning this QR code or using the link in the video description.